class, I recall electron withdrawing groups and how they affect acidity. So if we have, let's say, a carboxylic acid here, so acetic acid, and we add some base to, or well, what is its pKa? So its pKa is like around 4.8. So its conjugate base is going to look like this, right? But what if I added to that carboxylic acid a electron withdrawing group, let's say chlorine? What do you think the pKa of this compound is going to be in comparison to the acetic acid? Is it going to be more acidic or less acidic? What do you think? Well, the pKa of this guy is 2.9. And so that's telling us it's more acidic. Well, why is it more acidic? Remember that it has to do with the stability of the conjugate base. If the conjugate base is more stable, then the acid form is going to be more acidic. So what's going on here? Why is this guy more acidic? Well, we have what? Inductive effects. We have that very electronegative chlorine atom pulling electron density. And why is that a good thing? Well, because the electrons on this oxygen are being pulled to the other side of the molecule. And whenever you can get electrons to move around, it is a stabilizing effect. So why even worry about this? Well, because when we take a look at benzoic acid, like this, depending on the electron withdrawing group that you place on the ring, can also influence the acidity of our benzoic acid here. So if we just have, let's see here, if X, let's put it up here. So if our X was hydrogen, so just a simple benzoic acid, the pKa would be around 5. But if we change the X to a, let's say, a really, really strong electron withdrawing group, let's say a nitro group, the pKa of that is going to change to 3.4. So the acidity is drastically been changed. So you can put in all sorts of different, like we could even put in our chlorine, and that would give us a pKa of about 4. So the guiding principle here is that based off of this, the same concept applies to the benzoic acid derivatives. If you have a good or very powerful electron withdrawing group, it's going to pull electron density, or let's look at it right here. It's going to pull electron density that will stabilize the conjugate base and make it more acidic. I want to make one minor correction. I looked at the table a little bit more closely. Technically, it's not 5, it's 4.2. But the main idea here hasn't changed based off of that value. Okay? Just want to make sure we correct that. Now let's remind ourselves, how do we make carboxylic acids? So we're going to review what we've learned already, and then we're going to talk about different ways to do it, or new ways that you haven't seen before. So do you recall from chapter 9.9, if you take an internal alkyne and you treat it with ozone, and then you work it up with some water, Remember what you get? You're going to split this bond right here, and you're going to get 2 carboxylic acids. So if we go R1 and R2, we can look at it that way. Remember that from chapter 9? We also have from chapter 12, 12.10 to be exact, based off of the textbook. If you take a primary alcohol and you treat it with chromic acid, and then we have to add some acid, sulfuric acid, and some water, we will generate our, whoa. So there's 2 carbons, so that would have to be like that. Give us our carboxylic acid. Let's see, what have we more recently learned in Orgo 2? What if we have a benzene with an R group attached? And what if we treat that with the, there should be a 2 right there, chromic acid. Remember what's going to happen? We're going to replace that R group with a carboxylic acid. So this is a way to make benzoic acid. But recall, though, that this R group, there's a requirement. That R group has to have at least 1 benzylic hydrogen. So that right there is the benzylic carbon. And the way I drew this molecule, you can see that there is 1 hydrogen not shown. So that reaction would work. But what if I had a benzene derivative that looked like this? That would not work because when you look at the benzylic carbon, there's no hydrogen. So that can be anything really. You could draw it however crazy that you want it. Okay? You could put on it like a 3-member group. It just does not matter as long as there is a benzylic hydrogen. And the way I drew it, there's 1 hiding out. So that was what? That reaction was from chapter 17.6. Now, there's 2 more reactions that we need to discuss to make carboxylic acids, and they are with nitriles and with carbon dioxide. And so I'm going to clean this board, and then we can talk about those 2 new reactions. Another way of making carboxylic acids is if you take a nitrile and you treat it with some acid and you add some heat. What's going to happen is it's going to hydrolyze the nitrile into a carboxylic acid. So if I drew it a different way, I would have drawn it like this. So it's a very straightforward reaction. You have a nitrile, you add acid, add some heat, boom, you generate the carboxylic acid. Pretty straightforward. Another way is to use Grignard reagents, which is kind of cool. So if let's say we have a Grignard reagent that looks like this. And all we have to do is take that Grignard reagent and dump it over dry ice. You just get dry ice, and it's in the pebble form. And then you take this reaction, because remember, you have to make Grignard reagents. So this is going to be in an ether solution. And you just take that and dump it right over the dry ice. And then after you gather up the solvent in your reaction, you have to do a second step. And that's just going to be an acidic workup to give us our carboxylic acid. Isn't that cool? So the Grignard doesn't have to have the benzene. We could have just done a generic Grignard reaction right here. Treat it with the same conditions as up above. And what would we get? We would get our carboxylic acid. Now, when you look at this generic one, where's this carbon coming from? Well, it's coming from the carbon dioxide. So let's take a closer look at this mechanism right here. So you can see it a little bit better where these carbons are coming from. So here's our Grignard reagent. It's going to attack that carbon like that. So this is our step 1 right here. That's going to give us what? It's going to give us a R group attached to a carbon double bonded O, and then a O negative. And then what do? We do step 2, which is the acidic workup, which is simply, there's going to be the hydronium around. So this is going to come and do a proton transfer mechanism to give us our product. Just like that. Pretty slick. Now let's take a look at reactions with carboxylic acids. So if we have a generic carboxylic acid here, and we treat it with lithium aluminum hydride, and then do step 2, we do an acidic workup, what we generate is a primary alcohol. So overall, what's happening? We have this carbon right there. We are taking off the double bonded O and replacing it with what? 2 hydrogens. So this is a reduction. So we are reducing carboxylic acids to primary alcohols. Now, how does this occur? Well, we have a carboxylic acid, so we know it's acidic just based off of the name. When you take a look at lithium aluminum hydride here, we can represent it looking like this, right? And that's going to be negatively charged. We've seen lithium aluminum hydride act as a very strong nucleophile when it reduces aldehydes and ketones. But now we're dealing with the carboxylic acid, and it also acts as a very strong base. So there's 2 lone pairs there. So what you're actually going to generate when you treat carboxylic acids with lithium aluminum hydride is you're going to form the carboxylate. of the negatively charged carboxylate. So then how do we get from a carboxylate to an alcohol? What also is going on here? What did we form? We formed hydrogen gas. So that's going to bubble away. So that's going to promote the reaction to go, because you can't get hydrogen back after it bubbles out of the solution. And then you have the aluminum species right there. So the next part of the mechanism is going to use this piece right here to get us to where we need to go. So if I redraw the carboxylate like so, what happens is aluminum is going to, the word is called coordinate. It's going to coordinate with the carboxylate like this. So here's our aluminum. It has the two hydrogens there, and then we have a hydrogen there. And it's going to coordinate, which means this oxygen atom, because it has some lone pairs here, it can coordinate to that aluminum. Now it's a dotted line, so it's not saying it is a bond. It just gets really close to that aluminum and it feels an attraction towards it. And then we could also see that this is going to also have an attraction towards that hydrogen there. Now what's going to happen now is, as it's coordinated like this, we can break this bond. Whoa, messed up here. Let's move this negative charge over so that we can see this a little bit better. Put the negative charge right there. And it's actually this carbon atom that's coordinating with the hydrogen in that manner. Okay. Now what can happen here is this bond right here between the aluminum and the hydrogen is going to break and go like that. And then this pi electrons right here in the carbon-oxygen bond is going to go and form there. So what's the result of that? What's that going to look like? It's going to look like this. So there's the hydrogen. This hydrogen that I just drew is that one. And then we're going to have a single bonded O, and that has now formed a bond with this aluminum species right there, just like that. And what do we still have going on here? We still have the O minus. So we have that species. Now this species now is going to come in and collapse down. And now this is a good leaving group when the oxygen is attached to the nitrogen. So that's going to leave like so. So what have we generated? We have generated an aldehyde. So we said the product is a primary alcohol, but the mechanism is showing us that we now have a aldehyde. Now what's going to happen is you generate this aldehyde, but with lithium aluminum hydride being present, you can't just isolate this. You cannot isolate the aldehyde, because the moment you form that aldehyde, another molecule of lithium aluminum hydride is going to come in here and reduce this. So we can go back this way now. So if we put in another lithium aluminum hydride, We have seen this reaction before, where you have an aldehyde or a ketone reacting with lithium aluminum hydride, which will do this. It will add that hydrogen. We have our negative charge there, plus our aluminum species, and that would be negatively charged. Now what's going on here? Now we have this alkoxide, and can we see that? Let me just box it in right here. Draw that line. Okay, so now we have this carboxylate, and then what's going to happen? We have step 2, which is the acidic workup. And why are we adding an acid in the second step? To protonate that. So we're going to have a proton transfer to give us our alcohol. And it's going to be our primary alcohol. Just like that. So what would the proton transfer look like? I'm pretty sure all you know what that's going to look like, but just in case, for those people who want to see it, you're going to have your acid, and what's going to happen? That's going to come and grab that proton. So what we could do is say, hey, that one right there is the orange proton. Another way to do this reaction, or this transformation, where you can take a carboxylic acid and convert it into a primary alcohol, is using borane, BH3 in THF. THF is just the solvent, borane is the reagent. That does the same transformation. Now, it's not going to proceed by the same mechanism, but it's going to do the overall same transformation. Now, in organic chemistry, chemists will typically, if they have a carboxylic acid and they want an alcohol, they will use this reagent over lithium aluminum hydride. Now, why do they typically do that? Well, it's a chemoselective argument, because oftentimes when chemists have a molecule, they have multiple functional groups in their molecule, and they want to reduce just the carboxylic acid and not touch any of the other functional groups. So this example I'm going to show you here is, let's say we have a ketone, okay? And that ketone is attached to a benzene ring. But we also have a carboxylic over here. And our game plan is that we want to reduce just the carboxylic acid into a primary alcohol, but still keep the ketone. We need the ketone. So if you tried this reaction with lithium aluminum hydride, step 1, and then step 2, your acidic workup, would you reduce the carboxylic acid to the primary alcohol? Of course you would. But we have also learned that lithium aluminum hydride also reduces ketones into secondary alcohols. And that's not the product that we wanted. So instead, we would use the borane, so BH3 in THF, and what would we get? the ketone wouldn't be touched, and it would only reduce the carboxylic acid into the primary alcohol. And that's the main reason why chemists use the borane, because it is chemoselective. With some reactions that we have seen so far is when we take a carboxylic acid, we can reduce it into the primary alcohol. So what have we done when we look at oxidation numbers here? We see here that the carboxylic acid, this carbon right here has an oxidation number of +2. And then the oxidation number over here for that carbon is now a -2. Now, if you don't recall how to do oxidation numbers, you can review that in your textbook in chapter 12. Taking a look at some of the carboxylic acid derivatives and looking at their relative stabilities, the acid chloride or the acid halide molecule is very, very reactive. So it's very unstable. And because it's so reactive and so unstable, we don't find many acid chlorides in nature, in natural products. The same thing goes for acid anhydrides. They are also very, very reactive and unstable, and so we don't see those in nature very much. But esters, on the other hand, are very, very stable, and we see them in nature all the time. This molecule here is called isopentyl acetate. This molecule, if you were in my orgo lab, you would be making this molecule in lab. And the reason why I have you guys make this molecule, because it's really fun to make, because this is the molecule that's responsible for the smell of bananas. So you go into the lab and it smells like bananas the whole time. I feel bad for those people who hate bananas and it makes them sick, but it's a pleasant smell for some people, hopefully most people. And so I think UCF does that reaction as well, but I don't know for sure. But isopentyl acetate is a fun molecule to make. Amides are another very, very stable carboxylic acid derivative that you see all the time in nature. And amides are found in proteins and peptides. So remember how we were calculating the concentration of peptides, and you need to know the tyrosines and the tryptophans, the W's and the Y's, to calculate concentration. Right here, what I have is a very simple peptide, just 3 amino acids, alanine, serine, and phenylalanine. And you can take that and translate it into what the molecule actually looks like. And what I want to focus on right now is that you can represent the side chain. So we have a side chain in every for every amino acid that I'm representing with the letter R. So the R's are the side chains, and depending on what that R or the side chain looks like determines what amino acid you have. But the main point of this image is to show you, look, that right there is an amide. That is an amide right there. Amides are very, very stable, and we see them in our proteins. And if our proteins weren't stable, then we would cease to exist, because proteins give us function. It keeps us alive. And if these amide bonds The amide bond is right here and right there. Those amide bonds are very stable. So if we want to take, so this, what I'm going to say now is extra for those people who are planning on taking biochemistry in the future and need to know their amino acids. So in this particular case, alanine is a methyl group for its side chain. So that's alanine. Serine has a carbon here, CH2, then attached to a OH. That is the serine side chain. And then phenylalanine would look like this. Just like that. So starting to learn the structures of your amino acids may enhance your experience here in Orgo 2, but not entirely necessary. But it definitely will get you a head start for biochemistry if that's something you'd like to do. So now we're going to shift to nomenclature. It's one of those necessary evils that we are going to start naming acid halides. Okay, let's name acid halides. Let's say you have a molecule that looks like that. How do you name it? Well, first thing that I noticed that it is a alkyl halide. So this is a carboxylic acid derivative. So what I do is like, okay, what would the carboxylic acid version of this look like? And so all I would have to do is replace this bromine with a OH. And now I'm like, okay, what's that name? That's acetic acid. And this right here is a derivative of that. So I'm going to use some of this name to help me name this guy. So what you have to do, let's kind of color code this to make this a little easier to see. You're going to take away the ic, okay, and the acid. And you're going to replace those with replace it with a YL and the name of your halide. Okay. So we keep the ACET and we replace the IC-ic with a YL. And then it says you replace it, you add on the halide part. So what is that? That is a bromide. So that would be a acetyl bromide group. What if we had a molecule that looked like this? Well, I'm jumping the gun. What if we had a molecule that looked like this? Well, I see that that is a acid chloride, so it is a carboxylic acid derivative. So I just go back and look at this guy. Now, if you want to be consistent, let's draw it the same way. It doesn't really matter. We'll put the carboxylic acid right there. So how would you name this guy? That is a common name, so that's benzoic acid. And so the rule says get rid of the oic and the acid. We keep everything the same. That's not underlined. Benzo, like that. Replace it with the YL. Benzoyl. What's the halide? Chloride. Please, please, please don't name it benzoyl chlorine. It has to have the "ide" in it. You will see on standardized tests, you will see, hey, name that molecule, and you'll have an option of benzoyl chlorine. Okay? That's how we do it. Now, what if we have a molecule that looks like this? What if we have there? How do we, now what's different about this guy? Well, we have a ring now with the acid halide on the outside of the ring. So that is a derivative of this. To remember when we have carboxylic acids on the outside of the ring, how do we name it? Well, this molecule is going to be called cyclo. That's a 6-membered ring, right? Cyclohexane. We keep the E, and we just add carboxylic acid. Like so. Okay, so that's that name. But what do we do now? Here? Let's see here. Let's change it. Change colors here. You're going to now replace it with carbonyl halide. Carbonyl halide. So here in blue, that right there is going to be replaced with the pink. So that's going to be replaced with the pink right here. So this molecule's name, we're going to keep the green. So I'm going to write it underneath here because it is rather long. Cyclohexane. We're going to replace this blue with the pink, which is now carbonyl. And what type of halide do we have? That would be a chloride. Cyclohexane carbonyl chloride. And that right here is the name for that guy. Okay. Next, we are going to look at acid anhydrides. Now let's take a look at acid anhydrides. What if we had a anhydride that looks like this? Well, we know anhydrides are carboxylic acid derivatives. So we need to go back to the carboxylic acid that makes this, or it is a derivative of, so we can name it. So what I look at is I'm like, okay, I'm going to take that piece right there and draw it. And tack on the hydrogen. But pay close attention. What if I did this? What if I chose this side? What would that pink one have been? It would have looked like this. Those two molecules are the same. So this is a symmetrical acid anhydride. So what we're going to learn first is how do we name a symmetrical anhydride. So you figure out what is the carboxylic acid, and then you name that. And we know this guy is called acetic acid. So if we want to go to the acid anhydride, this one's easy. All you have to do is replace the acid word with anhydride. That's all you got to do. So the name for this anhydride, let's draw it again so we can see it better. So that guy is acetic anhydride. Pretty straightforward, isn't it? But now, things can get a little bit more complicated. What if we have a anhydride molecule that is unsymmetrical? How do we handle that? So let's take it and let's say we have a benzene ring. Something like that. How would we name that? Well, we've got to go back and look at each carboxylic acid that it was derived from. So I'll go like this. So that would give me a molecule that looks like this guy. I don't know about you, but aren't the markers today more squeaky than usual? So what's that guy called? That's benzoic acid. Let's test my luck with a different marker. And then this piece right here is going to be what's that guy called? That's acetic acid. So what's the trick here? We remember that we're going to get rid of the acid and replace it with anhydride. But now what you do is you just look at that part of the name and you write it over here in alphabetical order. So we have acetic, benzoic, and typically you don't capitalize the second one. Just redo that one. Benzoic anhydride. Pretty straightforward. How much time do we have? We are out of time for this lecture. So we will continue on naming our carboxylic acid derivatives in the next video. We'll look at esters and amides. And then we will even start naming some nitriles. Then hopefully we can start getting into some chemistry. Okay?